Why are 2D sphere diagrams so confusing? Imagine trying to draw a ball on a flat piece of paper and making it look just like the real thing. It sounds simple, but it's actually quite tricky. When we look at a sphere in real life, it's a three-dimensional object with a curved surface all around. But when we try to show it on a flat surface, like a piece of paper or a screen, we run into some problems. That's because a sphere exists in 3 dimensions, and a flat diagram only has 2. This difference causes distortions that can make understanding the shape difficult. A sphere is made up of points that are all the same distance from its center. It has a smooth, curved surface with constant curvature everywhere. When we try to draw this on a flat surface, we have to flatten the curved surface, which is impossible without changing some of its properties. According to a rule called Gauss's Theorema Egregium, you cannot flatten a curved surface like a sphere onto a plane without stretching or squishing it. So, any 2D drawing will either distort the angles, the size of areas, or the distances between points. This makes it hard to see what the sphere really looks like and how its parts relate to each other. Another reason these diagrams are confusing is because they lack depth cues. When we see a sphere in 3 dimensions, shading and shadows help us understand its roundness and curvature. In a flat diagram, these cues are missing, so circles on the sphere might look like ellipses or distorted shapes. Also, lines that are curved on the sphere, like great circles, might appear as straight or irregular lines in 2D. This can lead to misunderstandings about the shortest paths or routes on the sphere's surface, which are actually curved lines called great circles. Understanding the geometry of spheres is also tricky because concepts like spherical triangles and angles are different from flat triangles. For example, in a spherical triangle, the sum of the angles is more than 180 degrees, unlike in flat triangles where it always equals 180 degrees. Representing these differences accurately in a flat diagram requires careful explanation, which is often missing. Without this, it can be confusing to grasp how spherical angles and triangles work. Map projections add another layer of confusion. Different ways of flattening a sphere, like on maps, focus on preserving certain properties. Some maps keep areas accurate but distort shapes, while others keep angles but change sizes. Without knowing which projection is used, it's easy to misinterpret what the diagram shows about the sphere's true shape and size. In practical terms, when studying spheres in geometry, we often look at cross-sections, which are circles. But a flat diagram can't show the full volume or the curved surface of the sphere. This makes it harder to understand how the volume relates to the surface area or how the sphere behaves in 3 dimensions. That's why in fields like geography, aviation, or computer graphics, people use 3D models or interactive visualizations to better understand spherical shapes. So, the main reason 2D sphere diagrams are confusing is because they can't fully capture the 3-dimensional shape without distortions. These distortions lead to misunderstandings about distances, angles, and the true shape of the sphere. Recognizing these limitations helps us better interpret and use these diagrams in learning and real-world applications.